Okay, so we're going to look at some formulas involving springs.
What are those?
We're going to look at some formulas involving springs, and this ball is supposed to be bouncing up and down.
Why isn't it charged? Got one.
Okay, so you remember Hooke's law. Hooke's law, he's the guy that did all the spring stuff. Okay, so consider these springs. So it doesn't matter whether you are, and I'm going to try and draw a stretchy spring. So if you're a bald-headed skinny man pulling on a spring, or if you're a bald-headed skinny man pushing on a spring, or a bald-headed skinny man? I don't know anybody like that. Or if you happen to be a mass that is bouncing up and down. All of these springs follow the same law. That being?
Hooke's law.
Hooke's law.
What is Hooke's law?
Robert Hooke, I believe. So all springs follow Hooke's law. There he is there.
Look at that. Look at him.
He had a certain spring in his step, you might say.
That's like a one. That was terrible. That was good. Pretty well.
Mental note, work on that one for next year. All right, so Hooke's law relates the amount of force, F, that you exert on a spring to the distance, x, that the spring is either stretched or compressed. In other words, he wanted to know what's the relationship between force and distance. Now, you should have determined this relationship on Thursday already. Many of you discovered that the graph was a
direct,
which means it was a straight line. Is that what you found, Stefan?
Yes.
I know I saw Abby's, I think it was hers group. You guys was almost perfectly straight, wasn't it? Yeah. Yeah. We usually get pretty good results there. So your graph of force versus distance should have looked like this, which means we get a straight line, right? We get F is proportional to X. You should have had that the other day. F is proportional to X. Which means if you stretch it twice as far, you're going to need twice as much force. Which gives us the equation F equals Kx. Right? To go from a proportionality statement to an equation, we put in a constant of proportionality, the letter K, and we change it to N equals. And then the question is, what's the value of K?
4 or 5. 4.
Now, most of the time, the constant, because it's called the constant, is a constant, which means it's a number and it doesn't change, like pi or 4 pi squared or the speed of light or something like Avogadro's number. Very nice. 6.02 times 10 to the 23. Nerdfest 2012. Continue. My whole life is Nerdfest. Okay, so Hooke's law is, this is what Hooke's law really is. The force exerted upon a spring is directly proportional to the amount the spring is stretched or compressed. The force exerted upon a spring is directly proportional to the amount that the spring is stretched or compressed.
What happens when the universe reaches its outer limits? Like, you implode on itself. Nobody knows. I use the camera to find it. It would be like an eye, like an exam. No, then you use your camera. It originally exploded in like milliseconds. So you probably forgot.
Nobody knows. I don't.
How cool would that be, though?
It'd be cool.
When the universe goes to
Take a picture of it.
Let's go. Like, it's so like
There he is.
All
right, so the constant of proportionality is called K, and we call this the spring constant. Now, you should have determined the other day, I think you got 2 graphs. Did they have the same slope?
Yes. No.
I don't know how many of you graphed them on the same graph. Did anybody graph them on the same graph? Same axis? Did you? And were they 2 different slopes?
Yeah.
They were. So in other words, they had different spring constants, didn't they? So in this particular case, the one that I had graphed up here, this one here, if I were to find the slope of this line, I would find it to be 35
Newtons per meter.
newtons per meter. So the slope of that line is 35. In other words, the spring constant for that particular spring is 35. You probably had, did you guys find slopes?
No.
No? I probably should have had you find the slope. Okay? The spring constant gives us the amount of force required to stretch the spring a distance of 1 meter. Now, generally, springs aren't stretched a meter. Then after about,
Overstretched.
they become a wire, right? After. Yeah. So
When
they.
is that defined? When do they stop defining spring?
I don't know. That's a good question. How? I guess when it becomes to the point that it doesn't rebound back, I suppose, right?
I don't know. It's gone back a little bit.
It would be interesting to see or to know what's happening on a molecular level to a spring. I don't know.
More empty space.
I don't know. I'll have to look that up, I guess. Spring. Yeah, spring constants do tend to be larger numbers, relatively speaking, simply because you're having to stretch it a whole meter or compress it, right? So you guys should have found 2 different spring constants. In other words, the name constant is a bit of a misnomer because it's only constant for it's only constant for that particular spring, right? And its siblings, I suppose.
How do the springs move along?
Then you would need 35 meters to stretch it. To stretch it another meter. Doesn't matter how long it is, it's how far you're stretching it. Right? Okay, so quick little sample question here. Now, hold on here, don't write that down. So when a 6 kilogram mass is attached to a vertical spring, the spring stretches or compresses a distance of 40 centimeters. Find the spring constant. Pretty straightforward. We're finding the value of K. You got the question there on that sheet. How am I going to do this?
Can you use D for distance of X?
You could.
Yeah, why do we use X for D?
Why do you use D,
I don't
X,
know.
and H?
I don't know.
Well,
Wait,
you're
D
supposed to
is
teach your hard, you don't know.
displacement.
Maybe, yeah. D is displacement. So I'm going to use the force, which is going to be the weight force, because it's stretching it vertically. It's mass times gravity, 6 times 9.8, or 58.8 newtons.
Keep on shit him.
All right. Yeah, you saw that? Oh, good. That makes it good. All right, so F equals Kx, 58.8 equals K times 0.4. 147 newtons per meter. That's a pretty big number.
Not really.
That would be a pretty stiff, pretty strong spring, right?
Well, it's like 12 pounds on it.
Yeah. All right. Now, when you stretch a spring, you obviously do work to it. Where does that work go? We already know.
Someday.
When you raise something, right, it goes into potential energy. Same idea here, right? So consider the amount of work that you do on a spring with a 200 Newton per meter constant. This is sort of back to the notes here. I don't know how you want to do this. Yeah, sorry about that. The work is force times distance. Remember that the force is exerted. The force exerted is found by using Hooke's law. F equals kx. Right. So this F can go in there. Right.
Oh, it doesn't work. Well, you know what work is.
Now you'll notice, I wouldn't bother jotting that down. I wouldn't bother that. Okay. You'll notice that the distance goes up by 10 centimeters. The force goes up by 20. What's the average force exerted? Because the force is going to be more. Well, the average force is simply going to be 0 plus 100 divided by 2, or 50 newtons, right? Because, like, what force, if I'm trying to find out how much work, what force do I use? Because at the start, it's kind of easy, but as I get to the end, it's getting harder and harder. So which force do I use? Do you think the average force seems reasonable?
Yeah.
Seems to be.
Oh.
The average force, right? Yeah. Now, if we look at it sort of from a, oh no, I guess I'm not there yet, sorry. So how much work was done? We're going to use average force in this case here. I'm going to put a little bar above the F.
Where's the 50 from?
Average force. Remember we started with here on the little table of data? We started with 0 newtons. We went all the way up to 100. We took the average force. So if I use my average force in there, I'm going to have 50 newtons. Now, what distance would I use?
Average. No, full distance.
Full distance.
I thought it
Full
was
distance.
1 to 10.
Full distance. So 50 times 0.5, we're going to suggest that the work done here is 25 joules, which would mean also that 25 joules of energy is stored in the spring, right?
Yes.
25 joules of energy is stored in the spring. Now, I'm thinking that the next, I don't have the notes up here, but I'm thinking that the next slide is going to show me a graph. What's a graph going to look like in that? This is bugging me.
I know, it's so bad.
We would use W equals FD if it was a constant force, right? A constant force, what kind of graph would a constant force be if it was force and distance? A constant force would be like that, right? And F times D would be the area. Very similar to what we've done in the past. So would that be true for an increasing force? Absolutely. So if I were to go back to that graph, and I'm going to find the area under here, I'm going to find the area of that triangle. And Quinn, the area of a triangle is half the base times the height. The base is from 0 to 0.5. Half the base. When I say half the base times the height, could it also be half the height times the base? Base times height divided by 2. Isn't that not just, there's my height is 100, right? My height is from 0 to 100. What's the height divided by 2 going to be? It's going to be 50. It's the average, right? The whole thing all sort of fits together, right? It's 1/2 the base times the height, also 25 joules. What I'm getting at here is that the work is the area under a force times distance graph, right? So if the force is constant, it's a rectangle. If the force is increasing at a steady rate, it's a triangle. If the force is some sort of curve, well, then you're going to have to learn calculus and integrate.
What?
I don't know what that is.
I know. Megan, you might want to just hang on to Jordan there so he doesn't fall off the chair. You were. You were doing the lean. All right, so algebraically, what do we got here? Area is half the base times the height. The base was the distance. The height was the force. Let's just do this. The distance is x, so 1/2 x. The force exerted is kx. Where am I going with this?
So don't like with each other.
1/2 kx squared.
This is the formula, right?
That is a formula. And the area is the work, is it not? The area is the work. So the potential energy of a spring, which is the area, US, potential energy of a spring, is 1/2 kx squared.
What's U? U is
Potential.
U is potential.
Potential spring energy.
Potential spring energy, 1/2 kx squared.
I have potential.
I don't think. What? No.
I'm giving you a work period, Tuesday and Wednesday. You can use it as you please.
What's the dates? 29.
30th and 31st?
No, that's a
So 29, 30.
Okay.
of May
May 2012, Physics 40S.
on Earth.
Yes, on Earth.
Milky Way
In this
galaxy.
class, where
Milky Way galaxy.
All right. So I think you have this question as well, right?
We do.
If you do 24 joules of work in compressing a spring whose constant is 80 newtons per meter, how far is the spring compressed? I don't know. Is it 12?
So that means
How are we going to do this?
K
Well,
equals 80.
the 24 joules of work is going to be converted to potential spring energy, US, right? The K value is 80 newtons per meter. We want to know how far it's compressed, which is X or D if you prefer. I think it's a simple matter of going US equals 1/2 kx squared. Right?
What formula is that?
The one that I just derived, right? So the potential energy is 24, 1/2, 80 x squared. I would suggest take half of 80, which is 40, of course, and then divide by 40, 24 divided by 40, and then square root, 77 centimeters. Here's sample number 2. I guess it's number 3, yeah. A spring with a constant of 200 newtons per meter has been compressed 10 centimeters, 0.1 meter. How much work must you do from this point to compress it to the 0.4 meter mark?
Well, it's a tummy.
Well, can you just go 0.4 minus 0.1 and say, well, we'll just use 0.3 in our calculations? At first glance, you might think, that seems to be okay, right? Well, let me ask you this. Is the first 10 centimeters the same amount of force required as the last 10 centimeters?
Oh, we must take the average.
So can you just subtract those two? I don't think you can. Okay. Remember that the work done is the potential energy gain. So I'm going to prove that to you mathematically. But you can't just subtract the two.
Don't you split the leaf button or something?
Yeah, you can. So what I've done here is I've shown the USI, potential initial spring energy, 1/2 kx squared, 1 joule. I've got the final potential spring energy, USF, 1/2 kx squared, 16 joules. And I'll pause for a second. Yes. So what do you think I'm going to do next here?
You got a little great thing. You're gonna subtract that.
Subtract them?
Yeah.
So you need an average.
So the work required is the difference between the two, right? If I started off with 1 joule of compressed spring energy, and I do work to it, and I ended up with 16 joules, then I must have done 15 joules of work. I must have done 15 joules of work. So that's the correct answer. If I were to put in the 0.3, what would I have gotten? If I were to have gone 1/2 kx squared and I went 1/2 of 200 and then 0.3 squared, what would I have got?
Like 0.9 times 200 is like 180.
I would have got 9, right? 1/2 of 200 is 100. 0.3 squared is 0.09 times 100 would be 9. Okay? So doing it this way would have been wrong. Okay? You can't subtract the distances. I just showed it to you. Showed you once. It's because it takes more, the last 10 centimeters takes more force than the first 10 centimeters.
And you can't equally.
Okay? And in fact, your graph, if you were to look at it from a graphical standpoint, the graph would have been like this, and so you're actually finding the area of a trapezoid. Okay, so don't do that.
Get off.
All right. Oh. Okay, last bit, 15. Last little bit. Okay, what happens when things run into springs?
They get compressed and they go.
Kinetic energy is transferred to potential
Can
energy.
you compress a string?
Can you compress a string?
Yes. Yeah, you can.
No, I think we've tried that.
Yeah. Get around this way.
You could squeeze it.
You could compress it. Well, does that work? Would you get us straight?
All right, so think about a mass colliding with a spring like a bumper car or pogo stick or pogo stick.
What are those bubble cars?
Before the collision, would not all of the energy be kinetic?
Yeah.
Right? You're driving along in your bumper car
Maybe pogo stick.
or your pogo stick.
You're not driving.
No, you're bouncing.
No, you're not, because you're not looking.
Okay, so here's my little
Focus that sideways.
box, yes, my sideways pogo stick, and I'm running that sort of up and down sort of
Okay.
thing is a really bad drawing of a spring.
Oh.
Right. This is my little boxy thing running into the spring. So all of the energy is kinetic. Okay, now what about during the collision? Right? As the box thing runs into the spring and the spring is compressed a little bit, as you can see, right? The kinetic energy of the mass decreases as it does work to compress the spring, right? The box is doing work on the spring is storing up potential energy. All of that energy must be conserved. So ET, not the one that phones home, ET, total energy, would be kinetic energy plus potential.
I get it.
Spring's gonna ruin the test.
So ET is mv squared over 2 plus 1/2 kx squared. It's just the sum of two energies, really. Right? Okay, so all of the kinetic energy is being converted to potential. What happens when the mass is stopped, like it comes to rest?
It's back to
It's all potential, right? And then it's going to bounce back, exactly. Now, if the spring could somehow harness all of that kinetic energy and then give it back, then you would obviously fly off just as fast as you came in, right? That's not what happens.
What happens if the mass is like, you're like a big mass and then you push it down on the spring, but it's all the spring gets flat. Obviously, that you stay potential.
Well, then if the mass itself could be compressed, right? Like if it's like a bumper car, then the car itself would get compressed, right? Like the spring would no longer be compressing. The spring constant of the car would come into play, right? Okay, so that's just the same thing as before. At the end of the collision, all of the energy is transferred, and the kinetic energy becomes 0. And this is the key right here. Okay? The initial kinetic energy becomes the potential, the final spring energy. All of that kinetic energy, the initial one, is transferred to final potential. Or in other words, 1/2 mv squared is 1/2 kx squared. Has a nice symmetrical look to it.
Think about a lot of that. That's part of that.
That's the formula. How about you guys give this one a try on your own? What do you say?
Give it a whirl.
5 kilogram mass is moving at 5 meters per second. It strikes a spring bumper, having a spring constant of 50 newtons per meter. Find the kinetic energy of the mass before the collision. Find out how far the spring will compress. And find out the kinetic energy after compressing 0.8 meters. I know you should be able to do A and B.
Maybe a giant spring put it on.
Am I wrong? Can you do A and B?
Yeah.
Yeah? It's very similar to what I just showed you, right? How do we find the initial kinetic energy? 1/2 mv squared. I'm going to guess you guys all got 62.5 joules. Yeah? Feeling good about that? Well, let's have a look here at this part. Did you get 1.58?
Yeah.
You just did it right there.
Okay, so I think we're good A and B. The kinetic energy of the mass after compressing the spring 0.8 meters. So you got to figure out how much energy has been put into the spring, right? And then basically subtract that from the initial kinetic, I think, right? So the first step, would it not be 2? Well, I sort of done it in one step, I guess. So I'm going to say the E, I guess that's really ET. Total energy is our 62.5. The kinetic is what we're trying to find. The U is what we're going to know eventually. Okay, I'll whoa. Okay, so I'm going to put 0.8 in for my X. My 50 is my X. That's how much potential energy the spring is getting. And whatever's left over should be kinetic.